Welcome to week 13. This is going to be a lecture on flip-flops, which is part of the basic components of sequential circuits. What you're going to hear this week is about the following basic components, and more specifically the set-reset latch, or as we call it, the S-R latch, the data latch, or as we quickly call it, the D latch, and then we're going to talk about the D flip-flop. Now, the purpose of this week is to understand the internal construction and the behavior of those asynchronous S-R latches, and also to understand the external operation of D flip-flops. Before we proceed with a brief introduction for this week, let's first remind ourselves a few things. So, a combinational logic circuit is a memoryless digital logic circuit whose output at any point of time depends only on the combination of its inputs. So you've already seen a few things already in the past lectures which are related to this topic. You have seen arithmetic logic functions, and more specifically you've seen adders, subtractors, and everything else that you see over here. We've also talked about data transmission combinational logic circuits. This is what you got over here. And there are also other categories like the code converters. And what you should have been familiar with in real life is the example of BCDs, or as we call them, the binary coded decimals. So this actually is a term that refers to a scheme for representing decimal numbers by using 4 bits, and it can be well combined with a 7-segment lead like the one that you see over here. That is another example of a combinational logic circuit, which is memoryless, and its output depends only on the input combination. The only thing that it needs is LEDs or liquid crystal displays to display those 7 segments in order to represent a decimal number. Having that said, let's proceed with the introduction for this week, which is going to help us connect what we're going to be talking about next with what we've seen so far in DCS. You probably remember from the last lecture, before the Christmas break, that there is something called ALU, which stands for the Arithmetic and Logic Unit. ALUs perform operations inside CPUs. These are the basic operations. It's the binary addition and subtraction, OR, and XOR operations. These are done on 2 inputs that come here. So suppose there is bit A and bit B, which are given as input to this ALU. What happens is that based on the control unit, the ALU knows which operation to use. Is it going to be, for instance, a binary addition between A and B? Then the output will be A plus B. Is it going to be OR? Then it's going to be A or B, and so forth. Now, let's see step by step, remind ourselves how that works. So inside a 1-bit ALU, you have an OR gate, an AND gate, XOR gate, and a full adder. This is going to be the place where the operations between A, which is fed everywhere here, as you can see, and B is going to take place. Now, there is, of course, also this XOR gate over here. I recommend that you go back to the previous lectures and remind yourselves about how the full adders can work when it comes to using 2's complement. As you can see, there is the carry-in bit that comes in here, and there is also a carry-out that comes out here. Now, depending on what is passed to the control unit, which has here, as you can see, 2 different outputs, the multiplexer here is going to choose which result is going to be the output of the ALU. If the control unit says it's the first option, 0, 0 in this case for S0 and S1, then it will be the OR between A and B. If it's going to be the use of an adder, then things change. It's going to use the result of the full adder, and it's also going to use part of the control, as you will see in the previous lectures, to decide whether or not it needs to process B over here for reasons related to its complement. So that is a very simple model for the 1-bit ALU, and if we simplify things, then a CPU would be nothing more than just a series of ALUs here, connected, of course, with each other. What comes in is an n-bit word from the memory, and each of the pair of bits is given to each of these ALUs, and then the output that comes goes again back to the memory. And of course, this same control unit should be used here for all the ALUs. Now, a question that comes up next is, how do you store all these bits? The bits that come from the memory and the bits that go back to the memory. This is the main topic of this week and the weeks to come. Contrary to all the logic circuits that you've seen so far, which are combinational, the output depends on the inputs at any given time. You're going to see a new category of circuits. A category of circuits where the output depends not only on the current input, but also on the state, on a history, on the output from previous instance in time. Which brings us to this slide over here. So, a sequential circuit means that the output depends on the current status and the previous values or states of the inputs. Contrary to what we've been talking about so far, which was combinational circuits, where the current input defines the output. Now, how is that done? Well, assume this model over here. This is a combinational logic circuit. The output stems straight from the input. But what happens if you add feedback? This feedback loop over here. So by using this feedback loop, the result, the next state, goes through a storage element, and then from the storage element it can be retrieved and fed back to the circuit, which more or less models the sequential logic circuits. Now, a problem that arises is, how can you make sure that you will not fall into oscillations, which means that the previous output is not going to be indefinitely affecting future outputs. And if that happens, maybe you will be oscillating between two different states. There will be, for instance, some instability in the output. Well, you're going to see how this works next. Talking about storage elements, there are two very popular varieties of elements, latches and flip-flops. So a latch is a level-sensitive storage element, as you're going to see, and a flip-flop is edge-triggered storage element. At this stage, maybe it's not clear to you what exactly this means for both latches and flip-flops, but it will become clear during the class. Common examples of latches include the S-R Latch. S-R stands for set and reset. Then, as you probably remember from the last lectures, we can always use an enabling bit. So we got a variety of S-R latches with enabling bits. And then you got the D-latch, which you can also call the gated D-latch. Now, when it comes to flip-flops, you got, again, the D flip-flop and the D flip-flop with enabling.